We learned already about BFS, which is depth first search. And in this section, we are going to learn about BFS, some concept about BFS, and then what is BFS algorithm, and some properties of BFS. BFS, we call it breadth first search. So before I explain about the BFS, I would like to give more knowledge about graph, especially when you are dealing with the graph, and if you want to dealing with path. We learn about simple path. You still remember what is simple path? We learn about simple path. We have the simple path, we have simple cycle. So simple path means we want to visit every vertex and adds one time, or unique or distinct. There should be no duplication. We can make path graph. What is the meaning by path graph? Path graph or linear graph is a path with at least two vertices is connected and has two terminal vertices. Vertices that have degree 1, while all others have degree 2. So if you see this one, this is path graph because we have two terminal vertices. What does it mean by two terminal vertices? Terminal vertices means the vertices that have degree 1. So this vertex has degree 1 and this vertex have degree 1. Because there are two vertices that have degree 1, then I can say this is the path graph. Path graphs are often important in their role as subgraph of other graph, in which they are called as paths in that graph. So I can create some kind of subgraph in the path graph. For example, I want to go here. I know this is a graph. I know that this is a graph, and then I can make like this kind of path graph, and I can make also the subgraph. So let's say if I want to visit from this node to this node, there are several alternatives for the route. There are some alternatives for the path. And if I want to make a cycle, it means I will visit this node twice and so on. So it is a common graph, especially in the transportation. In our domain, industrial and management engineering, we can see a lot of this kind of graph in the transportation. There is another kind of graph. This is one example about bipartite graph or pie graph. Pie graph is a graph whose vertices can be divided into two disjoint and independent sets U, V. Okay. So this is vertices. This is another vertices. And every edge connects a vertex in U to one in V. So I have one vertex here. I can connect to another vertex. I have another vertex here. I can connect to this vertex. The bipartite graph are used extensively in online space. So you are now in the environment of online space, online shopping, online environment, online advertising, e-commerce, and etc. So this is one of the application if you are dealing with this kind of environment. In the bipartite graph, it is denoted as G, where you have U, it is a set of nodes or vertices. V is another set of vertices, and E is the set of edges on the graph. So for example, we can have many applications for this one. If you are dealing with the online shopping, if you deal with the recommendation system, I would like to know what is the review from user one about the item one. Okay, the user one give ranking 5 to item one. So the user one give 1 to the item 2. The user one give 0. Okay, what does it mean by 0? Maybe the user one never buy the item 3, and the user one never buy item 4. That's why this 0, and so on. So we can have the other user information and how they review the items that had been promoted in the online space. And also we can see another kind of representation. So if you are familiar with this matrix, we can convert this matrix into the bipartite graph, like this one. So the user is connected to this item, and then, okay, the review is 5, and the user is connected to this item, the review is 1. And you can see that this bipartite graph can represent what items are popular, and then what is the highest score or what is the average score for each of the item. Then as an online shop, we can try to figure out what can we do for our future marketing, for example. There is another kind of graph, we call it graph structure stack, GSS. In this graph, it is a directed acyclic graph. Directed graph, I think you know. Directed graph is a there is a direction between the nodes. Acyclic. Acyclic. It means no cycle. Okay. So there is a term acyclic, no cycle. So directed acyclic graph. Okay. And we can see this example. And in this example, you can see there are many nodes and there is a direction toward the root. So it means it is a directed acyclic graph where each directed path represents a stack. We can make this one as a stack. There are 4 kinds of stacks. So first is 7, 3, 1, 0. This is one stack. And then 7, 4, 1, 0. And then we have another stack, 7, 5, 2, 0. And there is another one, which is 8, 6, 2, 0. So what is the necessity of this one? We can create a kind of grammar, or this is the application for the natural language processing, NLP. It is a context-free grammar. Let's say I have a word, the little boy ran quickly. I know that the is an adjective, little is an adjective, boy is a noun. So in order to make this kind of sentence, it consists of adjective, adjective and noun, and then there is a verb and there is an adverb. So this adjective and singular noun we can accumulate or aggregate as noun phrase, and then this adjective and noun phrase can be accumulated as the noun phrase, and this singular verb and adverb can be regarded as a verb, and all of them belongs to one sentence. So we can make this kind of structure with the graph structure stack. We can also deal with the stack for graph traversing. I think you know when we are dealing with the tree. Okay, last time I mentioned to you, we have the tree for the graph, and we have another tree for the rooted tree. In a graph, we don't have any root. In the rooted tree, we have a specific root. And in the rooted tree, we learn some traversing. I think, yeah, on Friday we already learned pre-order traversing, post-order, and then, yeah, in order. So there are three of traversal mechanisms. In the graph, yeah, there is another mechanism. So this is one example of the mechanism. Yeah, you learn about DFS. It is one of the way to traverse among the nodes in the graph. But in this example, it is connected with other data structure with this stack. So in the previous chapter, we learned the graph traversing using DFS, depth first search. The idea is with graph traversing using stack. Oh, sorry, I think this is not the. Yeah, the idea is something like this one. You know the stack, right? When we are dealing with the stack, yeah, let's say I have this graph. You can define, for example, you want to know the starting. What is the starting of the vertex of the graph? I visit the S. So I visit S. And then let's visit the neighbor of S. What is the neighbor of S? It can be T. It can be U. So if I want to use the DFS, then I will select one, let's say T, and then I can select another neighbor. Then visit neighbors of that neighbors. So you can consider if you want to visit U or you want to first visit P. Okay. So after you visit P, yeah, you will check visit that neighbor. Okay, what is the neighbor of P? Yeah, it can be W, or maybe you want to search first the neighbor of the U. Okay, so the neighbor of T is U, and then after U, you want to select W, and then you select X. So it depends on how you select the sequence. And we can put it into a stack. Every time consider the neighbors of the last vertex visited. Let's say this is the last vertex, which is X. So after you have this stack, then you want to pop up to know the sequence. What is the possible sequence to visit all the nodes? Then it is a combination between the DFS and stack. You can use the DFS and stack. You can also use with Q. So the problem in the assignment is Q, and then you can extend the Q. I will check later about your assignment. It is totally open problem. So any solution is okay, because there is no correct solution for the assignment. Everything can be done. Maybe you want to create a new class, or you want to create a new function, or you want to create a list. Yeah, it's open problem. The same with the graph. We can connect the graph with stack. We can connect graph with queue. We can connect graph with array. We can connect graph with priority queue. So that's what I want you to do in the team project. You can combine several data structure and several algorithms. Because if you can understand one concept, let's say I understand graph, I understand stack, and if you can combine it, that will be enough for the team project. So in the previous chapter, we learned the graph traversing using DFS. We visit the neighbors of S, and then visit the neighbors of the neighbors in turn, and we want to use the Q. So let's say I start with S, and then first I visit the neighbors of S, and then the neighbors of T is, let's say I visit U, and then after I visit U, I want to visit another neighbor, which is V, and then I visit another neighbor, which is W, and then I visit another neighbor, which is X. So every time I visited the neighbor, yeah, I can remove using the Q. Now, yeah, I would like to mention another kind of traversing. We call it breadth first search. So you will see later what will be the difference between the breadth first search and the depth first search. In BFS, it is a traversal of a graph G, and it visits all the vertices and edges of G. Determines whether G is connected and computes the connected component of G. I think you still remember what is connected component. So in graph, we should have all the nodes connected. Okay. So there will be a graph like this one. It should be connected. And we are going to compute a spanning forest of G. The BFS on a graph with n vertices and m edges. N is the number of vertices, m is the number of edges, so it will take O n plus m. BFS can be further extended to solve other graph problems. For example, you can find and report a path with the minimum number of edges between two given vertices. So we can select what will be the best minimum number of edges. And we can also find simple cycle if there is one. It's similar with the DFS. If you look at the algorithms, it is similar with the DFS, but it is different in terms of the steps. Okay? In this case, it is different, but the first part is the same. What is the first part? We are going to put all the label for all U in the vertices. Let's set it unexplored. For all the edges, let's set the label unexplored. And then for every of the vertices, if the label is unexplored, then do this one. This algorithm is this one. Now you can see in this algorithm, we have a new variable, which is L. I can say L, let's say this is, maybe I can just say level. Okay. So level 0, or maybe you can just say list, it's okay. Okay. But in my case, it will be good if I can say level, but it is not clear in my example for the level. Let's say you will see it later. What is the meaning by level? So L0, we have a new empty sequence. So we can say it is a list. So it will be a place to save all the sequences. So the L0 will add a new vertex, which is S. And then we will set the label visited. And after we visit it, check if this is the initial variable I equals to 0. And then you will check. Do you know what is the symbol? In pseudocode, this means not. Okay. If Li is not empty, I equals to 0. So if L0 is not empty, because L0 we just add with one vertex, which is S, so it is not empty. Then we will make Li plus 1 as new empty sequence. So we will make L1. Okay. So at the first start we have L0. Now we have L1. For all V that is the Li elements, what is I now? I is still 0. Then we have the S. So the S is the starting vertex. And again, we will check the incident edges. So you know what is incident edges from DFS. If we have a node or a vertex, so the incident edges is the edges that connected to this node. If we have another edges, then it is another incident edges. And there will be many incident edges. And then if the E is unexplored, so if this one E, it is unexplored, then check what is the opposite. So if we have the node, this one is P, so the opposite will be the W. And then we want to get the label of W unexplored. So if it is not visited, if W is not visited, then we will set the label E as discovery. So this H will be discovery. And then set the label W as visited. So it is visited. And then we want to add the W into the Li plus 1. So the L1 will be added with W. And it will be repeated for all the incident edges. After we have the E, and then we have the next E, which is, for example, E2, and let's say we have another, which is W2. Okay. So we will do this repeatedly until all the vertex. If we finish with this one, then I will be added by 1. I will be added by 1. So I will be 1. If I will be 1, so we will check again. Li is empty because L1 has some nodes. Then we will make L2. L2 is new empty sequence. So we will check again with this algorithm. If L2 has been filled with a new node, then we will again do this loop. Okay. With the long pseudocode, we can have this Python code. Yeah, level. Yeah, and it is in the term of list. So I will make the S, the starting vertex, as the initial value of this level, while the length of the level is greater than 0. So it means if the list level not empty, okay, length, length, it is the size of the element. If there is no element, then stop, we don't need to do the loop. But if there is an element, you will do the loop. So the next level will be empty. And for every U in the level, we will check the incident edges. And then we will check what is the opposite. If V is not in the discover, then we will note this vertex as, this E is discovered, and then we will add the next level with a new V. Maybe it is good to see this kind of example. We have the same color. Okay, the blue color means the unexplored vertex. I put it as UV, and then the visited vertex VV, and the unexplored edge is UE, discovery edge is DE, and now we have cross edge. Okay. In the DFS, we have back edge. Okay, that's only just a terminology. So here we want to find the discovery edge, and if it is returning back, then it is the cross edge. Now let's assume we have this graph, and I want to start from A. L0, or the level in the first part, or the level 0, it will have only the A as the element. And then after we have the A as the element, I will explore for every neighbors. So first, I will check the L1, it is P. So P is noted as visited. And then here we have L0 is the A, and then B is regarded as L1. And then we have the AB as discovery edge. Okay, so this is what I explained the algorithm, the first part. Now we have the AB, and then now we have AC. Okay. Maybe it will be good if I explain in this. Okay. If you check, we have L0. Okay. We have L0 starting with the A, because L0 is a new empty sequence, and then we want to add the S, which is the vertex. And then we want to set the label S as visited. A is visited. And then we have I equals to 0. And then S, we want to check whether L0 is empty or not. It is not empty, so we will make L1. We will make L1, and then after we have L1, we want to check for all V in the Li element. So we want to check L0 element. So we have A, and then we want to check the all incident edges. We want to check all incident edges of V. So we can have the possible edges of A. So we have the possible is AB, and then we have AC and AD. Okay. We have possible edges is AC, AB, AC, and AD. And then all of them are first unexplored, but I put this one as the first state, which is discovery. And we know that the L1, if AB at the first time it is unexplored. Okay. The first one is unexplored, then, oh, sorry, this one. The label is unexplored, so we will check what is the W. AB is unexplored for the first time, so we want to check what is the W. The W, now it is the opposite of this A and B. It is the P. So we want to check whether the label of W is unexplored. Yes, P has not been visited. So we will do the set label E as discovery. Now it becomes discovery edges. And then set label W as visited. Set W, this one now P is visited. W equals to P. Okay. And then we want to add Li plus 1 with the W. So L1, now we will add with the W. W is P. Okay. After we finish this one, we will check another incident edges. What is another incident edges? We will check AC. AC is unexplored. Then let's check the E. What is the edges? Because it is edges AC, it is unexplored. So we want to check what is the W, which is the opposite. So the opposite of AC is C, and then check. C is unexplored? Yes, because C is unexplored. Now AC becomes discovery X, and then we will set the label C as visited, and then we add L1 with C. Next, we return back to this loop for all E in the incident as A. Okay? So it is still in this V. V is still A. And then there is another edges, incident edges. What is the incident edges? It is AD now. And then check if the AD is unexplored. Yes, it is unexplored. Then we check the new W. W is now P. And then we will check if the D is unexplored. Yes, it is unexplored. So we will check the AD. We will set it as discovery X, DE, and then we set the D as visited. And then we add D into this L1. Okay. So this is the step. So that's why you will, yeah, this is the step by step as I put in this board. So if we have the A to B, A to C, A to D, and we have A, B is explored, AC has been explored, discovery H, AD is discovery H, and B, C, and D are in the L1. What is next? So in the next, if you take a look on the algorithms, after we finish this, we will do the L I equals to I plus 1. Okay, so because everything in the A has been visited, so now we are visiting the I, which is 1. When I equals to 1, so we will check while L1 is not empty because we have B and C and D. So it is not empty. So we want to check for all the elements. Okay, so we will start with B. What is B? So B will have the incident edges. Okay. What is the incident edges of B? The incident edges of B is C. There's BC and there is another PE, but we are not dealing with PE at this moment. Why? I will let you know. We are checking the incident edges, which is the PC. Yeah, there's another possible which is PE and other. Yeah, we have another which is PE, but we will not consider it because we want to check the incident edges, and then let's find the label E, which is unexplored, which is the PC. It is unexplored, yes. And then we want to check the opposite. What is the opposite? The opposite of this B is E. Sorry. The opposite of B is BC is C. What is C? Now, if we are making this as okay, this one is unexplored. We want to check C, and then what is C? C is visited. It is. If get label unexplored, you can enter this one. But C has been visited. That's why we will do with the set label false. Okay. And so on. So all the set label cross will be noted as this dash line, and then yeah, you will see until the end. Okay, I think it is the time for us to do the review quiz. I think I will continue with this explanation on Friday. You can go to your e-class and then do the simple review quiz for today attendance check.